Hi, my name is Sriram Baireddy, and I'm going to be an electrical engineering senior at Purdue University this fall. I'm also a student in the Summer Undergraduate Research at Florida, or SURF program, here at the University of Florida. During the program, I worked at the Florida Institute for Cybersecurity Research, or FICS, where a lot of new and innovative research is being conducted to adapt our security measures to a rapidly evolving cyber world. My project focused on counterfeit electronic parts. The damage of counterfeit parts is highlighted by the estimates of the size of the counterfeit industry by the International Chamber of Commerce, or ICC. In 1990, they estimated a value of $100 billion, which increased to around $250 billion by 1995. This was then followed by estimates of $350 billion in 2001, $650 billion in 2008, and $1.8 trillion in 2015. It's not just the economy that's affected by this rapid growth. For example, in 2011, ice detection systems on the U.S. Navy's new Poseidon aircraft were found to be compromised by counterfeit electronic parts. Additionally, electronic tests revealed that their nuclear submarines had also been compromised. Coupled with the fact that counterfeit parts can have programmed backdoors that allow access, the effect on U.S. national security becomes a legitimate question.
There are many signs that an electronic part is counterfeit, but none of these indicators can individually determine the validity of the part. Currently, the standard practice is to have a subject matter expert, or SME, examine each part to determine its origin. This process is expensive, time-consuming, and can also be destructive. The goal of my project was to automate the detection of some of these surface defects that can be present on counterfeits, namely texture differences, marking displacements, and color variations. I used the Leica DVM6 to capture images of the 240 chips I was testing. It has interesting features like generating the 3D profile of the surface scanned and the ability to capture images at set locations repeatedly. This made it easier to quickly obtain all the images I needed to test the code I wrote.
The first step for my project was to make sure all the chip images had the right orientation and XY positioning, which is called image registration. This image is the reference image I used to register the subsequent images. My algorithm works by starting with the image that needs to be registered, which would be any of the 240 images I took. I use canny edge detection to distinguish all the edges present in the image, and then use a Huff transform to identify the actual edges of the chip. With the edges identified, I calculate their angles and rotate the image to make the edges parallel to the XY axes. Additionally, I add a displacement that aligns the edges with the corresponding ones in the previously mentioned reference image. The resulting black spaces are filled with relevant data from the reference image, creating a new image in the same orientation. This allowed me to make feature comparisons between images easily. Implementing image registration made the detection of marking displacement a lot easier. Markings refers to the identification markings on the surface of the chip. I use a normalized cross-correlation function that compares an image of the specified label against each image of a chip. The program works by first allowing the user to indicate all the markings they wish to compare. The correlation values for every possible positioning of the marking image on the chip image are calculated and then returned in a 3D surface. Clearly, the highest correlation value or peak on the surface corresponds to the location of the relevant marking on that chip. The calculated coordinates are compared to the marking's position on the reference image, and a pixel to millimeter scale is used to compute each displacement value. All the results are recorded in a text file for the user to read, while the displacements are shown visually on new images. Texture differences can occur when the surface of a chip has been remarked. The standard procedure of remarking is to sand off the original markings and repaint the surface, but this can still leave behind some signs. I used a local binary pattern, or LBP, function to identify the texture present in the image. My algorithm works by first splitting the registered image into 100 parts and sorting each subimage into one of 4 categories: markings, side edge, horizontal edge, or pure. I then use the LBP function on each of the subimages to obtain a histogram of the region, which is compared to a predefined golden standard for the corresponding category. If the difference is too large, the subimage is identified as smoother than usual and marked as a region of interest. I also binarize the image to clearly identify smooth areas around the chip edges. All these regions of interest can be re-examined by the user on newly generated images. Color variations can be caused by a variety of reasons, like burn marks or improperly removed markings. This program is more straightforward than the rest. I generate the color histograms of the reference and chip images. The distributions are compared using Kullback-Leibler divergence, which basically measures the variance between two probability distributions. If the variance is too high, I identify the values causing the difference and mark their locations on the chip image for the user to verify. These results are all just small steps towards the final goal of automating counterfeit detection. I'm currently working on training a neural network to intelligently identify scratches in chip images regardless of orientation or clarity. Another area to look at is improving the intelligence of the color variations program to allow for lighting differences and other physical sources of variation. This project has been interesting, and I hope to continue working on it and others like it in the years to come. Thanks for watching.